Approximating area, rectangular approximation method. Objectives. By this lesson, you should be able to explain why we are interested in approximating area on the curve, understand how to use rectangles to approximate area on the curve, sketch a right, left, and middle rectangular approximation over a given interval on a graph, use the formulas to find the right, left, midpoint approximation, given a table of values, understand when a rectangular approximation will be an overestimate or an underestimate for the actual area on the curve. So that's what we're doing today. So let's start off and talk about why. Why are we approximating area? To find out why, let's look at the example I set up here. So in this example, I give you the velocity function. So we have velocity feet per second, and we have time as our x-axis in seconds. And if I have a velocity function, it has some benefits. Like first, if I ask you how fast is the object traveling at time t equals 4, well, how fast it's traveling, that we're talking about the velocity. I have my velocity function. So all you have to do is go to 4. Look where it's a graph at 3. So 3 feet per second. Right? So time is 4. Look at the graph, 3 feet per second in units. So that's a benefit of having a velocity function. But what if I ask you about how far has the object traveled between 0 and 4 seconds? Right? That's a displacement, a distance formula. If we're talking about our kinematics, right? We're at the velocity form, we have to go up to displacement from 0 to 4. So that's from here to here. We're going to have to find the area of that guy. On the area of this guy. So right here, this is a trapezoid. And we shall know our trapezoid formula. We're going to use it a lot this semester. That is area equals 1/2 base times height times base 1 plus base 2. Where the bases are these guys. And the height is this right here. So that's one way to do it, to use a trapezoid formula. But I'm actually going to do it. I'm going to actually separate to make it a little easier for most people. Let's just do a rectangle plus a triangle. Right, so in this case that's 4 times the height is 1 plus my triangle here, 1/2 base times height. My base would be 1 to 3, so 2. My height would be 4. And in this case, I'm going to get 4 plus 4, which is 8. Now let's talk about units. I have seconds, and I got feet per second. So if we're multiplying the units, multiplying seconds times the height, which is feet per second. So we're going to have feet per second times seconds. And I'm going to get feet. So those are my units. And that happens to also be the distance traveled between 0 and 4 seconds, the area. So my answer here is 8 feet. And that's why we're interested in approximating area, to get to information like that. Now, what if the graph is a curve instead of a line? How do we find the area bounded between a curve and the x-axis? Like if I was going from 1 to 4, let's go 1 to 5 instead. If I want to find the area into that curve, it's not going to be nice. We're going to approximate it using rectangles. To make it easier, we'll use rectangles of equal width. So just to give an example, it's look something to this effect. We'll talk about this more in general, but it'll be something to this effect, where we're going to find the area of all these rectangles, and that's going to approximate for us the area underneath the curve we want. So you can see it's not a perfect area, but it's an approximation. This area right here, like I'm missing, right? It's a little under approximation. But that's going to be the idea. The idea is going to be, we're going to use rectangles to give a general idea of the area underneath the curve. To do this, we got to assume a couple things. First assumption, f(x) is continuous. Second, f(x) is positive. We are finding the area under the graph, the region between the graph and the x-axis on the interval from A to B, right? So like I showed up here, right? It's going to be a continuous function. It's going to be a positive function. And we're finding the area between the curve and the x-axis. A little terminology. A is usually the left endpoint when we have an interval. B is the right endpoint when we have an interval. N is the number of subintervals. So if we looked up here, my graph, I had 1, 2, 3, 4 subintervals. In this case, my N would have been 4. And if you want to figure out how long the width should be, all we're going to do is we're going to use this tiny formula right here. We're going to do the endpoints, subtract the endpoints over how many subintervals you want, and that'll give us delta x, which is the width of the rest of each rectangle. So for a quick example up here, I went from 1 to 5, and I had four sub intervals. So in this case, my delta x would have been 5 minus 1 over 4, 4 over 4, which would have been 1. So the length of all my subrectangles should have been 1. Or of all my widths should have been 1, sorry. And they were, right? 1 to 2, 2 to 3, 3 to 4, 4 to 5. Okay, so that's the general terminology. Now let's talk about more in detail how we use these things, what different types of approximations we could use. So the first type of approximation we're going to talk about is right endpoint approximation with n rectangles. So we're just going to do a general case real quick. So the estimate area in the curve between f of x and a. So let's just say, instead of being 1, let's say this is a. And let's call this b. So we're going to try to find the area underneath that curve. So we're essentially trying to find the area right here of underneath this curve. All of that. Essentially what we're trying to find. So let's talk about the rectangles. So when we draw rectangles, we start on the left-hand side. So it's if we do an interval, let's say this from here to here is our delta x. Right, to our width. We're going to try to keep it the same. So here's our delta x. Same thing over here and over here. Now, in this case, you notice how it says right endpoint. So since we're doing right endpoint, we're going to start on for a little rectangle right here, we're going to start on the right hand side. So right there, and then go straight across. Same thing with this one. Start on the right hand side, go straight across. Same here. Same here. And same here. Now notice on the last couple, they go past the graph, right? But I got to hit this rectangle here, so I got to make it a full rectangle. So you can see a couple of my rectangles fall below the graph, a couple of them fall above the graph. This is called right-hand approximation, where we make our rectangles based on the right-hand side. So go across on the right-hand side. Now, if I was to find the area of this, right, what we do is, well, if you notice, all these are delta x's. So we have delta x times, in this case, that if I'm doing rectangles to delta x, I need to find my height. So right here, it's going to be, this point right there is going to be my x value, which I know it says 2, but we don't know it's 2. But we know what it is really, that point right there is going to be a plus where my delta x is. So that's the a value. Welcome to calculus. And then remember how to find the y value? You plug it into the formula. I don't really have a formula, so it's going to be f of a plus delta x. So this little triangle rectangle right there, there is this going to be delta x, my width, times my height, which is f of a plus delta x. So you can do the same thing with the next one, right? So like that, my width right there is delta x, that's easy. My height, that point right there, well, you got to find the x value first. Again, that's not necessarily 3. It's a plus delta x, also known as a plus 2 delta x. That makes my y value, plug it into the formula, which we don't have, so we just put f of a plus 2 delta x. And keep on doing this, right? Who knows how many triangles we have in between. In this case, I could count, but in theory, it could go on forever. Then we stop, let's say we stop here. We'll just say this point right there is a plus n delta x. And I'm not sure how many n's we have. So my point right here is a plus n delta x, comma, f of a plus n delta x. So it makes the area of this little rectangle right there. The width, delta x, times the height, f of a times a plus n delta x. We can make this a little nicer. Factor out all the delta x's. And we get delta x times f of a plus delta x plus f of a plus 2 delta x plus dot 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 f of a plus n delta x. So that's my area. My area approximately is all of this. It's the width times all the heights added together. Or for short, I always do this personally. I find the area of each little rectangle. Or if you want, if you're fancy, you can use the summation notation, because all of this is just a summation. It's just the sum of, let's say j equals 1, right? So we're going to add f of a plus j delta x, because that's where we're adding all the delta x's together from that function. And we're going all the way from 1 to all the way up to n. It's kind of hard to see there. Why did it highlight? To n, right? That's my n. So that's where we're stopping. We're going to have all these functions until we get to the very end. The summation notation, or the official way of doing a right-hand approximation, we actually has a special name for this, which is right-hand Rn, where n is the number of subintervals of rectangles. If I see R3, for example, that means, okay, then let me do right rectangular sum approximation with 3 rectangles. So that's the way we're going to read this. And that's the right-hand side. If you notice, that was our right-hand approximation. But there's actually more ways to approximate. So the one we just did right now is a right approximation. So I give you a graph like this, right? And our rectangles are on the right-hand side. I could also do left approximation. We have the same graph, but we start on the left side now. And then we can also have midpoint approximation, where if I give you a graph, we actually start in the midpoint of our things. So we'll use the midpoint to branch out. Again, we'll talk about each one of these in detail in a second, but there's 3 of them. They're all kind of done slightly the same way. Midterms are a little different, but you can do a right rectangular approximation, a left rectangular approximation, or a midpoint rectangular approximation. So let's get into it. Let's do an example. So here, they want to calculate R4, which is a right rectangular sum, approximation sum with 4 rectangles. L4, left rectangular sum with 4 intervals, and then midpoint rectangular sum with 4 intervals. On the function f1 over x on 2 to 4. And actually, for the sake of ease, let's go to 1 to 5. You'll thank me later. Okay, so let's talk about how we do this. So 1 over x, let's look at the graph first. It's a reciprocal function, which all know and love. Looks like that. But we're only going from 1 to 5, so we're only focused on the positive quadrant. So that's why I have them down here. So we're going to do R4, do L4, and we get to do M4. So we are x and y. It's a sketch, it doesn't have to be perfect. And we're going 1, 2, 3, 4, 5. Now we can start off with the right rectangular sum. So first let's figure out how big our width to be. Actually, that's to start. Let's figure out delta x. Now all these all want 4. Remember the formula is b minus a over n was our formula, where b and a are endpoints, and n is the number of rectangles you wanted, so 4. So 5 minus 1 over 4, 4 over 4, which is 1. So the length of all our rectangles should be 1. Our width should be 1. So if I start at 1, first one, then we'll go 1 over, which will be 2, and 1 over that, which is 3, 1 over that, 4, and then 5. Now right here we're doing the right rectangular approximation, so I want rectangles that are on the right side. So sometimes I think it helps if you show the, let's color in what we're looking for, right? Our area is this right there, so recoloring it. So we're starting on the right side. So our little rectangle right here, we're going to start on the right side, so right here. That's the approximation I'm going to use. And then same thing with 3, so on the right side. That's the approximation I'm going to use. 4 on the right side, go across, and 5. So those are 4 rectangles we're going to use to approximate that area length of the curve. Now all we have to do now is find the area of those 4 rectangles. So I like to go old school. Let's find areas. Right, so the area of this one right there, this is base times height. We generally call this the base. So that's delta x, which we know is 1. The height, a little more fun. Right, so the height is this point right there. So how do you find that point? Well, we have the x value is 2. So if you want to find the height, you got to plug into the formula, which in this case is 1 over x. So that point right here should be 1 and 1/2. Sorry, 2 1/2, sorry. Right, x value is 2, plug into the formula, you get 1/2. So my height is 1/2. So I'm going to have 1 times 1/2 plus, sending for the next one, right? This is 1. My height, we'll plug it into the formula. That point is 3 1/3. Again, just using the formula. So the area of this rectangle is going to be 1 times 1/3. Then just sending for the next one, that is 1. Height here is going to be 4 1/4. So height is 1/4. And then finally the last one with this 1. That point right there is 5 1/5. This again, just plug it into the formula. So I get 1 times 1/5. So that's a long way of doing it, quote unquote long way. That's what I like to do. I just like to do it, just like find area of each one. Right here I get 1/2 plus 1/3 plus 1/4 plus 1/5. And I could solve that, plug in my calculator or whatever, but you get an answer. And that's our R4. Another shortcut way of doing it is, if you notice, every single one's going to have, these are all delta x's. So a shortcut way that some people like to do is to factor out the delta x, and all you have to do on the inside is add up all the heights. So I know it's going to be 1, so it'll be 1 times that. Both ways work, right? You could think about it as this one plus height 1 plus height 2 plus blah 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 height n. Either way works. I've always preferred just doing it the long way. Now let's do the same thing with L4, right? Same graph. Just a little sketch here. 1, 2, 3, 4, 5. Right. Starting at 1. Remember, the area I'm looking for is all this stuff. It's a nice approximation. And this time, we're going to be doing the left approximation. So we're starting on the left-hand side. So I'm going to start at 1. That's the left-hand side. And then you're going to go across to make the rectangle. Right, then we start at 2. Start on the left-hand side. Go across to make the rectangle. Start at 3. And start at 4. So those are 4 rectangles that you need to decide. So I'm doing the left-hand approximation, starting on the left-hand side. See those dots there. Right, and then this one, same idea. If we want to do L4 approximation, just find the areas. So you can use the shortcut if you want, still works, or you just find the area of each rectangle. Right, height here, since I'm starting on that side, you know what that point is. That point is 1, plug it into the formula. 1 and 1. The point right here would be 2 and 1/2. Always mess that up. The point right here would be 3 1/3. And the point right here would be 4 1/3. If I want to find the area of this guy, it's just going to be the width, which is 1, delta x, which is 1, times the height, left-hand side, 1, plus the next one, same idea, 1 times 1/2, plus 1 times 1/3, plus 1 times 1/4. If I added this up, I'd get 1 plus 1/2 plus 1/3 plus 1/4. And mine should be something like that. If you notice, the answer there is 1 plus all that stuff. This one, answer up here is just 1/2 plus 1/3 plus 4. This is going to be way bigger. If you look, you can tell that by looking at the graph. This is an over approximation, right? My rectangles are above the area. I should be finding that above that orange or peach. Over here, my rectangles are below it, so this will be an under approximation. How about midpoint? Midpoint is generally considered the best approximation. So we're going to do M4 here. Right, so let's draw a graph. Ooh, not my best. 1, 2, 3, 4, 5. Again, this is where you could see, right, we're trying to find the area of all this guy. Helps a little bit when you're trying to draw the rectangles. So in this case, I want midpoint, M4. So how does that work? Well, midpoint between 1 and 2 is 1.5. So that point should be like up here. And that's where you draw your rectangle. So it'll be like this. Why is that important? Because that's going to be your height. Doesn't look very midpoint, I'm sorry. But that's going to be your height. So it's going to change height a bit. So then we do the next one. Halfway between 2 and 3 is 2.5. So around there, that's where I draw my rectangle. Halfway between 3 and 4 is 3.5. That's where I draw my rectangle. And then 4.5. So you can see it's the midpoint. You can see on most of these, it's a little bit above, a little bit below. So it's a little better approximation because it's more evened out. So how do we do this? Same idea. Find the area of each one. Now, I know it has 1.5, 2.5, 3.5, but the width is still the same. That doesn't change. My width is still delta x, which in this case was 1. What does change is the height. So, right, I'm using this point to find my height. That point right there is 1.5 is the point I'm using, and my height, plug into the formula. In our case, 1 over x, so it's going to be 1 over 1.5. I know, ugly, right? That's also known as 2/3. And then same thing over here. That point right there will be 2.5 and 1 over 2.5. So that's this little thing's going to be 1 times 1 over 2.5. Plus, same thing here. 1 times the height, which is 3.5 and 1 over 3.5. Plus the final one right there. That is 1 the width, and my height's going to be 4.5 and 1 over 4.5. So 1 times 1 over 4.5. And that's your answer. 1 over 1.5 plus 1 over 2.5 plus 1 over 3.5 plus 1 over 4.5. And that's our M4 approximation. So that's the approximation of that area of that curve using the midpoints. Right, so that's how midpoints works. You have to find the midpoint of your little rectangle there, and then use that to find your height. And again, all you have to do to find height is plug it into the formula, if you have a formula. So next question is, what if we don't have a formula? Well, that's what's going on right here. So we want us to calculate R6, L6, and M3 given the following table values. So remember, R6 is right rectangular approximation, so using right side. L6 is left rectangular, and M is 3. So let's go through this one by one. So let's do R6 first. So first, let's figure out what they want our width to be. Or delta x. So remember, that formula is b minus a over n. In this case, we're going from 1 to 13. So 13 minus 1. Let's say it's our a and this is our b. Over 6. So 12 over 6, which is 2. So our delta x is going to be 2. So what does that mean? That means we want to go for our rectangles to be 2 across. So we're going to start at 1, we're going to go all the way to 3, right, and our delta is 2. And then we're going to go 3 to 5, again 2 across, 5 to 7, 7 to 9, 9 to 11, and 11 to 13. Right, so those are our rectangles. We have this one right here, we have 1, 2, 3, 4, 5, 6 rectangles here. Now, keep in mind we're doing R6. Very important here, right? Because remember, the way we find a rectangle, very simple, base times height. So, my base is 2. What's my height? We're doing R, right? So it's going to be 4, right? Here's my f of x. The height is 4. So if I was going to make a little rectangle here, this is 2, and my height is 4 for this guy. On this one, it's going to be 2 times 8. On this one, it's 2 times 4. Then we have 2 times 10. And then 2 times 8. And finally, 2 times 4. So we get 8 plus 16 plus 8 plus 20 plus 16 plus 8. We get 32. Plus 24, so 32 plus 24 plus 20, so I get 96. That's kind of it. Find a right. So same thing we did before, just find a rectangle. So in this case, we wanted to space 6 rectangles. So we did the formula to find the width as 2. So 1 to 3, 3 to 5, 5 to 7, 7 to 9, 9 to 11, 11 to 13. And then we're doing the right Riemann sense. We're going to use 4, 8, 4, 10, 8. 4 and 4. And that's what it is. I just do one by one. Now again, the shortcuts, you can pull out the 2 and do some things, but I just like doing the old-fashioned way. Next, let's find L. L6. Right, we already know what our delta x is the exact same thing. It's just going to be 2. So it's actually the exact same rectangle, but now we're starting on the left side. So if we're doing this right here, we're going to start on the left side. So my height's going to be 2. So 2 times 1. Right, we're going to go 2 across, 2 across, 2 across, 2 across, 2 across. And we're doing the left side. So for this rectangle right there, we're going to use 4. For this one, we're going to use 8. For this one, we're using 4. For this one, remember, it's 2 times the height, which is, we're doing the left side, so 10. And then finally, my width is 2, my height is 8. Again, we're using the left side. Right here, I get 2 plus 8 plus 16 plus 8 plus 20 plus 16. So 32 plus 16 plus 20 plus 2. So I get 70. Hope I did that correctly. So I get 70. I always do that. Sorry, guys. So you get 70. So R6, L6. Right? Same idea. Find a rectangle. One of them I start on the right. You start on the left side. So that's why I only went to the left ones. I skipped the last one. Other one, R6, I start on the right side. So I didn't use the first one. I used all the rest. Now let's talk about M3. So let's make it a little nicer. Let's erase all this. Or most of this. So M3, I'm going to do that in green. Down here. Well, first our delta x is different. Then I want 3 things. So it's still going to be, what is it? 13 and 1. 13 minus 1. But now it's only over 3. So it's 12 over 3, which is 4. So my delta x is going to be 4. So we're going to go from 1 all the way, add 4 to it, to 5. Then we're going to go 5, add 4 to 9. Those purples had me messed up. So 5, 4 is 9, and then 9, so 13 is 3. So notice how it's broken up by 3, just like we wanted. And in this case, my width is 4 for all of these. Now keep in mind, we're using the midpoint, right? M3, midpoint. So what's the midpoint of 1 and 5? Well, 3 is. So remember, use the height, so 4. So I'm going to use 4 on that one. The one right here, right? Again, use the midpoint, 5, 9. The midpoint is 4 again. And then right here, 9 to 13. Okay, so distance is 4. What's the height? Use the midpoint, 11, which is 8. So 4 times 4, 4 times 4, 4 times 8. I get 16 plus 16 plus 32. So I get 64. So that's how I do M3, L6, and R6 on the table. I look at the exact same thing for me. It's like, here's my rectangle. Right, here's my rectangle. My width is 4. My height is the midpoint, which is also happens to be 4. So for me, it's kind of the same thing. It's just doing it with the rectangle now. Probably, I wouldn't recommend coloring it in. It just makes it funky, but that's the idea. Okay, last thing. How can you tell if something's an over approximation or under approximation? Given a strictly increasing function, so to tell if it's over or under approximation, all depends if it's increasing or decreased. If it's an increasing function, the left endpoints will give you an underestimate. So let's just draw a picture, right? Let's go from 1 to 5 or 6. If I'm doing a left endpoint, just draw it. So it'll be like, left would look like this. Notice it's my graphs are there below the actual curve. So left endpoint would be an underestimate. A right endpoint though, so on the right side, a little hard to see, but you can see, notice you're above it. So if you're not sure, always just draw it. But if it's an increasing function, left is underestimate, right to overestimate. If it's a decreasing function, it's going to be the opposite. Again, if you're not sure, just draw it. So look, I'll do the left one. Start on the left. Those are an overestimate. If I did right endpoints on this one, So on the right side, you notice to be below the graph, right? So right would be underestimate. So that's how I do. I just look at it, see if it's increasing or decreasing. I just draw a practice one real quick. Tell me if it's if it's under or overestimate. But that's a general rule. Increasing, left is under, right is over. Decreasing, left is over, right is under. If you're not sure, just draw real quick. It takes 2 seconds. And so this shows. Okay, one last thing. Right? So we know how to find the approximation of the curve, right? As we've been doing. But how do you find the exact area? Well, let's kind of tie everything together. The way you find the exact area, well, the best way to that's what it shows by an example. So this is this function here. We're going from 1 to 6. If we only do 2 rectangles, you can see I'm way over. Right? This is the area I want. I'm way over that. If I break down to 4 rectangles, well, I'm a lot closer. Still over, but a lot closer. If I go to 6, I'm even closer. So if you do n is like 100, or n is 1,000, or just get bigger and bigger and bigger, or if you just take a limit. So that's how you can get the exact area. You're going to take the limit of all these things. Tie it back to calculus, right? Take the limit of all these things and you can get the actual area. So if you take the limit of the right sum and the left sum, if you take the limit of the right sum, it's to match the limit of the left sum, to match the limit of the midpoint. And that'll equal the actual area. We call that area in the curve a Riemann sum, because that's the guy that discovered it. So, a Riemann sum. That's the lesson.